guys, we're picking back up with section 6.3. The first video went long, so we cut it. All right, so the beginning part of 6.3, we learned how to do some binomial calculations. Now, on your formula sheet, you'll see formulas how to find the mean and standard deviation of a binomial distribution. So remember that we said that a binomial distribution or a binomial variable is a special case of a discrete random variable. And we talked about formulas. How do you find the mean of a discrete random variable? Okay, well, what we said there was before, we said to find the mean, also called the expected value, okay, you just take the individual values times the probabilities, and then you sum them. Now, this formula will still work for a binomial because a binomial is a discrete random variable. All right, and we saw this more complicated formula, how to find the variance. We have to take the, also that's called var x. Okay. We could take the sum of the individual x's minus the mean squared times the probabilities. So that formula will still work for the variance. Okay, but there's two easier formulas that we can use if we know a distribution is binomial. Okay, so here is the formula we can use for the mean, and again we can call that expected value. Just take the number, the fixed number of trials times the probability of success. And here is a simpler formula how we can find the standard deviation. Okay, now both of these formulas apply just to the binomial. Okay. These will also work, but they're harder to calculate if we do it this way. Okay. So as an example, think about why this is the formula for the mean. All right, if we flip a fair coin 10 times, how many heads would you expect on average? Well, since the probability of getting a heads is 0.5 and we're flipping a coin 10 times, we would expect the mean number of heads to be 5. So there's the n. Okay, there's the p. All right, so when we multiply those, we get 5. All right, so this formula makes sense in an intuitive nature. Okay. So going back to the previous note card, and the example, let's see, just gotta find it. The Mrs. Desai's example. Okay, that was on page 9. Okay, let's remind ourselves what that said. Okay. She had a 10-item multiple choice quiz. So n equals 10. And the probability, if the student's guessing, remember the choices were A, B, C, D, E on each question. So the chances someone would get that right just by guessing is 1/5. Whereas a decimal, that would be 2/10. All right, so to find the mean, all we do is we take 10 times 0.2. All right, so 10 times 0.2 is 2. On average, we would expect a student to get 2 correct just by guessing. All right. So we found the mean. Now, how are we going to find the standard deviation? We're going to use this formula. Big square root n, so there's your 10, times the probability of success, which is 0.2, but you have to add in another term. You have to do the probability of failure. So if 0.2 is the probability of success, 0.8 is the probability of failure, because 1 minus 0.2 is 0.8. All right. So if we simplify this, we already know that 10 times 0.2 is 2. Then you multiply that times 0.8 and you get 1.6. So let's take the square root of 1.6. And that is 1.2649. All right. So 2 questions correct would be the average, and the standard deviation would be 1.2649 questions correct. All right. So for this particular example, I want to show you something. Okay, let's make a histogram of this particular problem. Okay, so the number of questions a student could get right are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. All right, and let's put the binomial probabilities into list 2. So I'm going to do that. I'm going to go up to L2. I'm going to go to distributions. I'm going to go down to binom PDF. Okay, there's 10 trials. The probability of getting one right is 1/5. All right, and the X value is going to come from the number in list 1. Okay. So if we look at this, we said 2 was the expected, 2 was the mean. Look at the probability there. There's a 30.2% chance that a student gets 2 correct. This is the biggest number. Okay? This is the biggest number. There's no coincidence that it happens at the mean. Now, if I made a histogram of this data, and let me turn plot 1 on here, histogram, list 1, list 2. I could do a zoom 9. It's probably not going to come out very well. But if I change my window, we're going from 0 to 10, so I'm going to change that from -1 to 11. But I'm going to scale it by 1s. All right, and I'm just going to make that from 0 to 0.4 and scale by 0.05. Okay, now let's graph it. All right. So this bar represents 0. Okay. The height, if I hit trace, the height of that is 0.107. So there's a 10.7% chance that a student would get none right. There's a 26.8% chance a student would get 1 right. All right. There's a 30.2% chance that a student gets 2 right. Notice that the biggest bar happens at the mean. Okay? The biggest bar happens at the mean. And then what happens after that? Okay, the bars get smaller and smaller. So the important distinction here, for this particular example, the p was less than 1/2. All right. So here's a general statement. If p is less than 1/2, the histogram is going to be skewed right. If p is greater than 1/2, the histogram will be skewed left. And if p equals 1/2 exactly, the histogram will be symmetric. All right, so let me change this a little bit so you can see it. All right, let's say that the probability that a student guessed correctly was, let's go back here under our list. Let me change that. Let me clear this. Okay. All right, so let's change that from 1/5 to 4/5. Let's say that, all right, the teacher changed this, and there's only one wrong answer. So like for instance on question 1, let's say E was the wrong answer. So a student would get credit for answering A, B, C, or D. All right. And if I'm going to paste that, oh, I have to be an L2. That's why it gave me an error. Hit enter. There we go. All right. Now, if P was 4/5, look at all these numbers. Now the biggest would be at 8. Because if I change this, 4/5 would be 0.8, so the mean would be 8. We would expect most people on average to get 8 right. All right, now if I did the histogram again, look at how that changed the histogram. Now it's skewed left. All right, let's change it one more time. Let's change the p-value to exactly 1/2. All right, so before we do it, if this was 1/2 instead of 1/5, this would be 0.5, that would be 0.5, and this would be 5. So the expected number that someone would get right was a half. Say it was a true-false test. All right. And look at the numbers now. Okay. Now, the probability of 5 is the biggest because that's the mean. And if I looked at that graph, go ahead and look at that histogram. It's perfectly symmetric. All right. So why does this happen? Let's think about why this happens. All right. You know that there's 10 trials, but if the mean is 2, the biggest bar is going to be at 2. All right. So if the biggest bar is at 2, there's only 2 bars to the left of that. But because there's the 1 bar and then there's the 0 bar. But you still got a whole bunch more numbers to cover. Okay, so these other bars have to gradually go down from there on out. All right, so if the probability, if the p-value is low, okay, it's going to be the other bars on the other side have to kind of compensate out for that. So that's why it'll be skewed right. That's why the histogram is skewed right. And that's what this bottom part is saying. Okay, that is what this entire section is saying. We expect that the biggest bar will be close to the value of the mean. Okay. Right. Now, we can also do something else. When n gets really big, the binomial probabilities, okay, or the binomial distribution starts to look more and more normal as long as n gets big. All right, as long as n gets big. So this says as the number of fixed trials n gets larger, the histogram of a binomial distribution looks more and more like a normal distribution. All right, it's going to be most accurate when the p-value is close to 1/2 and n is relatively large. So if p is fairly close to 0.5 and the fixed number of trials is relatively large, then we can use normal approximation to approximate binomial if we have to. All right, so we can actually use this normal approximation if this is true and if this is true. All right, so as long as those criteria are met, we can use normal calculations instead of binomial if we would like to. All right. And that's what's called the large counts condition. And there's another condition that the textbook talks about. It's called the 10% condition. So what this says, all right, when taking a random sample of size n from a population, all right, when we take a sample size of lowercase n from a population of size capital N, we can use binomial, okay, to model the count of successes in the sample as long as the population size is bigger than 10 times the sample size. Because when we take someone out of a population, okay, generally we do not throw them back in to be part of the sample again. All right, so we're actually sampling without replacement. That's what we're doing. We're sampling without replacement. All right. And since we're sampling without replacement, technically the probabilities change from person to person, but they change very, very minimally. And as long as this is true, then it's okay. Then we can still consider a binomial distribution. All right. So we have one more type of special distribution to talk about, and that is the geometric distribution. So geometric distribution, it's another special case of a discrete random variable distribution. Here's the catch though. All right, with binomial, when we did binomial before, I'll just put it up here. When we did binomial, we always started our x. You can have zero successes. Okay, we started our numbers at 0. And then it went on for a fixed amount of numbers. Okay, like in the last example, 10. Okay, the geometric works a little differently. Okay, we actually start, you can't have 0 here. It actually starts at 1. But the catch is it goes on forever. It goes out to infinity. Okay, so it doesn't have the same conditions as the binomial does. It doesn't have 4 conditions. Okay, there's actually only 3 conditions. So if you think back to the binomial, we had the binomial. The only one that's not valid anymore is this gnome. There's no more fixed number of trials. You still have success or failure, that's one of the conditions. Each trial has to be independent, that's still one of the conditions. And all trials have to have the same probability of success. So it does have those 3 conditions, but the fixed number of trials is now out. Okay? That's what the first sentence says. All right, works a little differently though. So it says a geometric, and I'll talk about why it's called the geometric distribution here in a second, but it says a geometric setting arises when we perform independent, not trials, but trials of the same chance process and record the number of trials it takes to get the first success. Okay. Right. So when we start this, you can't start on a 0th trial. You have to start on the first trial. So if you get a success on the first trial, you're done. Okay. So here's some formulas that we're going to use. And we'll talk about why they are what they are when we get to the examples. All right. It's actually, you don't really have to memorize those. I'll show you an easier way. And here's how we would find the mean of a geometric distribution. All right. Geometric distributions are always skewed right. All right. And always the biggest bar is always the first bar. We do have 2 calculator commands, which I'll show you as well. So let's go ahead through this exercise. It says, it is estimated that 45% of people in fast food restaurants order a diet drink with their lunch. Find the probability that the fourth person orders a diet drink. So if we think about this, all right, or we should say the probability that the fourth person in line is the first person who orders a diet drink. So this person ordered a diet. This one did not, this one did not, this one did not. This was our first success. Okay, that's the first success. So that probability is simply the 45% that was told to me. Okay. Well, these three people did not order a diet drink. All right. So the probability that the first person did not would be 1 minus this. It would be 55% that they did not. What about this person? Same thing. They did not. What about this person? They did not. Okay. So the simpler way to do this is to do 0.55 to the third power times 0.45. So what does this represent? 3 failures. That's the probability of 3 consecutive failures. And then here's your success, because the success happens on the fourth person. All right. So kind of coming back up to this formula, let's look at it. This 1 minus p, that's the probability of failure. Okay? And here they have k minus 1. So we would do 4 minus 1 here. Because if the first success happens on the fourth person, that means we have 3 failures before. 4 minus 1 is 3. And then the success happens. All right. So the way we would write this, we would say the probability, we have to give it a variable. I'm just going to call it y. Probability that y equals 4. Okay, I like to actually write it like this. Fourth equals 0.55 to the third times 0.45. And we can do that on the calculator very, very simply. 0.55 to the third times 0.45. All right, so this person is 0.0749, roughly. There is a 7.49% chance that the first diet drink ordered happens on the fourth customer. So what does y actually equal? Y equals the trial in which the first diet drink is ordered. So we can say that y is a geometric distribution with, okay, there's no symbol, it's not like a b, like binomial, okay? So I'm just going to tell the reader y is a geometric distribution with a probability of success of 0.45. Right. Now, think about why these numbers could hypothetically go out to infinity. You could have 1 million people say, no, I want a regular soda. And on your 1,001st person, they could be a diet drink, a diet soda. Okay? So let's kind of think about this in terms of a histogram. Okay. Now, technically, we should make list 1 go out to infinity. Okay, but I'm just going to leave it as 10. I'm just going to leave it up to 10 real quick so you can see it. All right. So here, but we don't start at 0, we start at 1 on a geometric. So I'm just going to go 1 to 10, excuse me. All right, now how to do this in the calculator. If we go to our distributions menu, right underneath the two binomials, or actually slightly underneath the binomials, you'll see geomet, which stands for geometric. So if we go geometric PDF, the probability of success is 0.45. And the x value is actually coming from list 1. Okay, so let's think about this. All right, the probability that the first person orders a diet drink is simply 0.45. Okay, it's simply 0.45. The first person comes up and says, I want a diet drink. What's the chance that happens? 0.45. What's the chance that the second person is the first person who orders a diet drink? Well, the only way that happens is if the first person does not order a diet drink and the second person does. So to figure that one out, that would be a failure, then a success. Look at that, 0.2475. What about the next one? All right, if the third person is the first person to order a diet drink, then that means you would have 2 failures, then a success. Okay, when you multiply decimals, every time you do this, the number gets smaller. Okay, so if we look back in our list, that's why as we go down here, the decimals get smaller, because every time you're multiplying by another 0.55. Okay, so like this one is 0.45. This is 0.45 times 0.55. This is 0.45 times 0.55 times 0.55. So on and so forth. When you multiply by decimals, the numbers get smaller. Okay. Now, if we were to plot this, let me just graph it. Okay. The first bar is always the biggest. All right, so let me take this up just a little bit. Let me take it up to 0.5 so you can see it. All right, so in a geometric histogram, the first bar is always the biggest, and it's always skewed right. All right. If we go over to 4 here, that's that 0.0749. So that's the first part of the question. It says also, find the probability that the first diet drinker of the day occurs before the 5th person. All right, so what does that mean? Before the 5th person. So for the second part of this question, before the 5th means y is less than the 5th. Well, just like in binomial CDF, being less than 5 is equivalent to being less than or equal to the 4th. Right. So we can do this several ways. Okay. We can add up the heights of the first, second, third, and fourth bar. We could do that. Okay. Or there's another way. Just like there's a binomial CDF, there's also a geometric CDF. So if I go under my list here, on list 3, if I go under my distributions, there's this thing, letter F is called geometric CDF, which stands for cumulative. So if I enter that, 0.45, the x value comes from L1, and paste, okay, we can simply look here. Okay, so if I were to add up 0.45 plus 0.2475 plus 0.1361 plus 0.0749, it gives me this number, 0.9085. All right, so there's a 90.85% chance that the first diet drink will be ordered on or before the 4th person. Okay, that's what it means. There's a 90.85% chance that the first diet drink ordered will happen on or before the 4th person in line. You can also use a shortcut formula. Okay? Look at this formula up here. It says the probability that y is greater than k equals this. All right, so coming back to that, if I wanted to find the probability that y is greater than 4, okay, let's look at the formula. It says take the failure rate raised to that number. So the failure probability is 55%. Raise that to the 4th. All right, so if y is greater than 4, let me figure that out. So if you take 0.55 to the 4th power, that equals 0.0915. In the calculator, that's what I just did, 0.55 to the 4th. So y is greater than 4 means 5 and higher. So when we do that, what I'm doing, that formula is a quick way to add up the 1, 2, 3, 4, the 5th bar and all the bars out to infinity to the right. All right, it's actually an infinite sum. So when we do that, we get 0.0915. But these two things are complements. Notice that. They're complements. So if I wanted to find the probability that y is less than or equal to the 4th trial, I would just do 1 minus 0.0915, which would give me 0.9085. Okay, so we can use this. This is kind of a shortcut formula. Sometimes it's hard to remember. It's not on your formula sheet. All right, so if you're unsure whether that's the correct formula or not, then just stick with your geometric CDF. Okay, stick with your geometric CDF in your distribution menu. Okay. And I think you guys probably understood this, but just in case you didn't, the probability that y is less than or equal to the 4th would mean the probability that y equals the 1st plus the probability that y equals the 2nd plus the probability that y equals the 3rd plus the probability that y equals the 4th trial. So you could add them up individually. Okay, you could do geometric PDF for that, PDF for that, PDF for that, and PDF for that. So you could also add them up individually. Or like we said, that's like adding up all the first 4 individual bars. All right. So we're almost there. We're almost there. We got one more page. So here's the second exercise. It says, in New York City at rush hour, the chance that a taxi cab is available is only 15%. All right. So, part A, how many cabs can you expect to pass you for you to find one that is available? Okay, or how many cabs does it take until the first one is available? All right, so that's actually a means question, but before we do this, let's make sure that this meets the geometric conditions. Okay, so we have by, we're going to skip gnome, e, o. So are there 2 outcomes? Well, either a taxi cab is available or not. Okay, so that's success and failure right there. Is each cab independent? Yes, it is. Each cab is independent. One cab being available doesn't mean another one's not going to be available. Okay. Do all cabs have the same probability of availability? Well, according to this, it does. The probability that a cab is available is 0.15. Okay. So it meets the 3 conditions. Okay. So let's let y equal the trial at which the cab becomes available. So if we start to list this, we can list y's and probability of y's. All right, maybe the first cab is available. What kind of chance do you have that the first cab is available? Well, that's 15%. You have a 15% shot that the first one that passes you or comes up to you is available. What about on the second trial? So on the second trial, what does that mean? That means that one was taken. There's an 85% chance that the cab failed to stop for you, but then you succeed. So that would be 0.85 times 0.15. All right. What happens if it's on the third trial? That means that two cabs were not available. Each of those had a 0.85% probability, but then the third one was yours. Okay. And then you could keep doing this on and on and on out till you could be standing all day, infinitely many cabs. All right. So part A, they're actually asking for the mean. How many cabs can you expect to pass you to find the one that's available? So one of the formulas on the previous page, to find the mean of a geometric distribution, it's real easy. You just do 1 over p. Okay. So in this case, it's 1 over 0.15. So if I do that, 1 divided by 15%, or 1 divided by 0.15, is 6.667. Okay. So what does that mean? On average, it takes 6.667 cabs until one becomes available. Okay. Now, geometric is different than binomial. If this was binomial, then the biggest bar would be somewhere between 6 and 7. Okay. This is geometric, which we know is always right skewed, and the first bar is the biggest. Okay. Part B. What's the probability that the third cab is the first one that's available? So here I'm trying to find the probability that y equals 3. So rather than put this into the calculator, y equals 3 means that 2 cabs are going to pass me because they're not available. So that means 2 failures and then a success. So 0.85 squared times 0.15. Okay, so that's 0.108375. And the last question here on this exercise, part C. What's the probability that more than 10 cabs pass you? So more than 10 means greater than 10. Well, we can use the shortcut here on this particular formula. Okay? Or, I'm going to use the shortcut here in a second. Or, what does y is greater than 10 mean? That means 11 or more. Okay? So this also means the probability that y is greater than or equal to 11, which is going to be the same thing as 1 minus the probability that y is less than or equal to 10. So if you use this version, then you can use this part right here, the second part of that. That would be the geometric CDF. But the formula is a shorter way to go. So what's the probability of failure? Well, the probability that a cab passes you is 85%. All you got to do now is raise that to the 10th. All right. So if I take 0.85 and raise it to the 10th, I get 0.1969 if I round. So there's a 19.69% chance that you're going to have to wait on more than 10 cabs till one becomes available. But it's New York City, it's rush hour. Okay? Sometimes you get that. Now, just to verify that that's the correct answer, we could do it this way. I could go 1 minus geometric CDF. Okay, chance of success is 0.15, sorry. Okay. The x value that I care about there is 10. Notice, exactly the same number, 0.1969. So this part is adding up the first 10 bars on the geometric histogram, but we want the right tail. So we have to subtract that total from 1. So one last exercise on geometrics here. It says a well-traveled state highway has its traffic lights green for 82% of the time. If a person traveling the road goes through 8 traffic intersections, complete the chart defined, what's the probability that the first red light occurs on the kth traffic light? Okay. So here, what's the probability that the first red light is the first? Well, if 82% are green, I guess I should underline that in green, what's the probability of red? What's the probability that I get red? Well, hopefully you say, well, that's 18%. Okay. So as I come to the first light, what's the probability that that first light is red? Well, it's 0.18. Well, what happens if the second light is the first one that's red? Well, that means that the first light had to be green, and then I have to get a red. So that's 0.82 times 0.18. What about if the first red light happens on the third one? That means I have a green light twice, so I have to raise that to the second power times the 0.18. Okay. But we know there's a quicker way to do this. Now let's fill out this chart. Just go under our list here. It also asks me about cumulative probability. We're only caring about up through the 8th light. Okay, so let me go in here and delete list 2. All right, so we're defining success to be a red light, so just realize that. Okay, so the probability that I get a red light is 18%. The X value is coming from list 1. Okay. So let's fill this out. So the chance that my first red light is the first one is 18%. The chance that the second light is the first red light that I come to is 0.1476. Chance that the third light I come to is the first red light is 0.121 according to my data. And I have 0.0992, 0.0814, 0.0667, 0.0547, 0.0449. But not only that, remember our calculator also has a geometric CDF, which stands for cumulative probability. So go up to L3, go to geometric CDF. The P again is 0.18. The X value comes from list 1. And paste. So if I want to find cumulative probabilities, all right. If I take 18 plus that number, I get 0.3276. Realize there might be some rounding differences from the calculator. All right. And if I keep looking down here, I get 0.4486, 0.5479, 0.6293, 0.696, 0.7507, 0.7956. So we did parts A and B. We found the probability that the first red light happens on each of these. All right. So there's an 18% chance that the first light I run into is red. There's a 14.76% chance that the second light is the first light that I come to that's red. All right. So on and so forth. And these cumulative probabilities, what's the probability that the first light I come to as red happens on the second trial or before? It's a left tail. Okay. So there's a 79.56% chance that I hit my first red light on or before the 8th trial. Okay. So let's answer this question. All right, we can do C two ways. All right. So this was part A, that was part B. The probability that the person will hit the first red light after the 8th traffic light. All right. So what's the probability that this distribution, we'll just call it X, happens after, which means greater than, the 8th traffic light? Okay. So if we use our formula, all right, we take the probability of failure. Well, to us, failure is green. We take 0.82 and raise it to the 8th power. If I do that on the calculator, I get 0.2044. Okay. But what does this mean? After the 8th? Well, on this diagram, after the 8th would mean add up the 9th bar, the 10th bar, the 11th bar, and so on. Well, if I add up the first 8 bars, this cumulative probability tells me what the sum is. All right, so to figure out this other part, okay, to figure out what this number is when I get out to infinity, okay, all I would have to do, this is going to be the same thing as 1 minus the sum of these first 8. So it's 1 minus 0.7956. It gives you exactly the same number, 0.2044. So the probability that X is greater than 8 is going to be equal to 1 minus the probability that X is less than or equal to 8. And we find this part, we could find that with geometric. And that's what this number is right here. It's a geometric CDF. We could find this, because we just did. That's what this value is right there. So hopefully that made sense, all right? Hopefully you understand how you find the mean and standard deviation of a binomial. You understand how you can approximate binomials with normals. Learned about those two conditions, the large counts and the 10% condition. We'll get more into that a little bit later in the course. Okay, and you understand about the geometric distribution. Okay. Now, I told you why. I told you that I would tell you why things are called geometric. All right, so like if we have just a brief aside. So if we have an arithmetic sequence, for instance, here's an example of an arithmetic sequence. 3, 7, 11, 15, 19. So you're adding the same number each time. That's why it's called arithmetic, because you're adding. Okay? But with a geometric sequence, I'll give you an example of a geometric sequence here. Okay, I'm just going to start at a number. All right, here's an example of a geometric. Okay. What's different about that, instead of adding, you're multiplying. You're multiplying by the same number each time, but right, the numbers are getting bigger and bigger and bigger. So the reason why this type of distribution is called geometric, okay, is because we start with 0.18. And then what we do is we do 0.18 times 0.82. Okay, so we multiplied this by 0.82. And then we took that result and multiplied it times another 0.82. So we got to take 0.18 times 0.82 times another 0.82. And that's why this thing is called a geometric probability distribution. Because every time I go one more light, that means I went through another green. So I got to multiply, when I go from here to here, I need to multiply times another 0.82 every time. Start with 18, and I have to do 18 times 0.82. Then 18 times 0.82 times another 0.82. So that's why it's called geometric. Hopefully that helps.